December 15th, 1883. Bay City, Michigan. The engineering calculations from visiting European railroad specialists would never fully capture what they witnessed that winter morning. American factory workers, building steam-powered lifting machines using methods that defied everything European crane design said was necessary for efficient railroad operations. Through the foundry smoke and hammer strikes of the Michigan industrial floor, massive steel derricks took shape with specifications that seemed wasteful to European observers. No lightweight iron sections, no precisely calculated minimum tolerances, no focus on immediate cost savings per European engineering doctrine. Yet they moved loads with power and reliability that European hand-operated cranes could not match. In European railroads, 15 men with pedestal cranes required days to clear a single 20-ton derailed car. Each wreck clearance was essentially manual labor, ropes, pulleys, and patient effort that left victims freezing while rescue operations crawled forward. The Americans were operating with engineering philosophy the Europeans had never imagined economical. Steam power, massive overbuilt components, safety factors 3 times mathematical requirements, lifting capacity that reduced wreck clearance from days to hours. 8,000 miles from European workshops, the most decisive crane revolution in industrial history was revealing itself, not in elegant efficiency, not in cost optimization, but in the systematic over-engineering that connected raw American power with permanence, European precision, never imagined possible. The Pennsylvania Railroad freight train had been traveling at 42 miles per hour when the rails buckled beneath 3 feet of December snow. Engineer William Morrison felt the locomotive lurch sideways at 11:15 that night, then watched helplessly as 5 cars accordion folded behind him in a thunderous cascade of splintering wood and screaming metal. By dawn, 40 passengers and crew members lay trapped beneath twisted steel and frozen timber, their voices growing weaker with each passing hour. Railroad Superintendent Charles McKenna arrived at the wreck site with the established protocol. 200 men armed with ropes, pulleys, block tackles, and teams of draft horses. The European method, proven across thousands of miles of British and German railways, required systematic dismantling of each car by human muscle and mechanical advantage. McKenna had supervised dozens of similar operations, watching crews methodically separate tons of debris piece by piece, while rescue operations stretched across days of backbreaking labor. The mathematics were brutally simple. A typical derailed freight car weighed 20 tons when loaded. Using rope and pulley systems, 20 men could generate enough mechanical advantage to lift and reposition such loads, but only after hours of rigging, positioning, and coordinated pulling. Each movement required careful planning, with crews working in shifts around the clock while winter temperatures claimed lives beneath the wreckage. European railroad authorities had perfected this system across decades of practical experience. British railways employed hand-operated pedestal cranes mounted on flat cars, machines that could eventually clear derailed equipment through patient application of human power. German engineering manuals specified exact crew sizes, rigging procedures, and time estimates for various types of railroad accidents. French railway companies had standardized the equipment lists: manila rope of specific diameter, hardwood blocks rated for calculated loads, and teams of Percheron horses trained for coordinated pulling operations. The consensus among international railroad experts was unanimous. Major wreck clearance required time, manpower, and systematic methodology. Any attempt to accelerate the process through mechanical innovation would prove both expensive and unnecessary, since existing methods had successfully cleared thousands of accidents across European railway networks. But 800 miles west, Daniel Parmelee Eels stood in his Bay City factory examining the morning telegraph reports with different eyes. The Industrial Works Company had built steam powered excavation equipment for Michigan copper mines and Ohio coal operations, machines capable of moving tons of earth and rock through the precisely controlled application of steam pressure. Eels had watched his mining shovels operate in conditions that would destroy lesser equipment, their massive boilers generating the sustained power necessary for industrial excavation work. The telegram from Pennsylvania described a scenario that Eels recognized immediately: tons of dead weight requiring rapid repositioning under emergency conditions. His mining experience had taught him that steam power offered advantages no amount of human labor could match: infinite precise control, sustained operation regardless of crew fatigue, and lifting capacity limited only by the size of the machine itself. Eels walked across his factory floor that morning, studying the massive steam shovel under construction for a Minnesota iron ore operation. The machine's revolving superstructure could rotate 360 degrees on its base, while steam cylinders provided the precise control necessary to position heavy loads within inches of their intended destinations. The boiler generated enough pressure to power continuous operation for 12-hour shifts, with fuel consumption that made economic sense even for the most demanding excavation contracts. The engineering challenge was obvious, but not insurmountable. Adapt steam shovel technology for railroad wreck clearance. Such a machine would need to travel on railroad tracks, reach accident sites within hours rather than days, and lift locomotive-sized loads with the precision necessary for rescue operations. Most critically, it would need to operate reliably under emergency conditions when mechanical failure meant human death. Eels began sketching specifications that morning, calculating the steam pressure, boiler capacity, and structural requirements for a railroad crane capable of lifting 20 tons at full extension. The numbers revealed both the challenge and the opportunity. Such a machine would cost approximately $8,000 to build and equip, while existing wreck clearance methods required only $200 worth of rope, pulleys, and labor costs per operation. Pennsylvania Railroad's chief engineer had already performed the cost analysis, concluding that Eels's proposed steam wrecking derrick represented a 40-fold increase in capital expenditure with no corresponding improvement in operational effectiveness. European engineering consultants reinforced this assessment, arguing that mechanical complexity introduced unnecessary failure points into operations that human muscle power could accomplish through proven methodology. The criticism focused on practical concerns. Steam boilers required skilled firemen, complex machinery needed specialized maintenance, and the proposed derrick's weight would limit its mobility across railroad networks designed for lighter equipment. European authorities questioned whether American industrial enthusiasm was creating solutions to problems that proper planning and adequate labor could solve more economically. But Eels had seen the accident reports that revealed the deadly mathematics of existing methods. Average wreck clearance time across American railroads, 72 hours for major derailments. Winter operations extended those time frames even further as crews struggled with frozen rigging and equipment failure in sub-zero temperatures. The human cost was measured not in dollars per operation, but in lives lost while rescue teams worked with tools that had remained essentially unchanged since the construction of the first railroad lines. The question facing American railroad engineering was whether steam-powered machinery could accomplish in hours what human labor required days to complete. The answer would determine not just the future of wreck clearance operations, but whether American industrial innovation could build machines powerful enough to lift locomotives as easily as European cranes handled freight car components. James Sullivan arrived at the Industrial Works Foundry before dawn on January 8, 1884, carrying blueprints that defied every principle of efficient crane construction he had learned during 20 years of mechanical engineering. Eels had specified main boom components using 6-inch thick steel I-beams, when European calculations called for 3-inch sections, boiler pressure ratings of 200 pounds per square inch, when 120 would adequately power the lifting mechanisms, and bronze bearings, the diameter of dinner plates where standard iron bushings would suffice. Sullivan spread the drawings across his workbench and began calculating material requirements that seemed to violate basic engineering economics. The proposed derrick would weigh 45 tons when completed, nearly double the 25-ton estimate that rational design principles suggested. Every component specification exceeded mathematical necessity by factors that European engineering manuals would classify as wasteful excess, yet Eels insisted on construction methods that treated each derrick as though it would operate continuously for decades rather than years. The foundry crew assembled that morning included German immigrants who had learned precision metalworking in the industrial cities of the Rhine Valley, Irish workers who had gained steam engineering experience on Great Lakes shipping operations, and American machinists who understood the brutal operating conditions that mining equipment faced in Michigan copper country. Sullivan addressed them in the practical language of men who built machinery intended to work rather than simply meet specifications on paper. The boiler construction alone revealed Eels's over-engineering philosophy in action. European crane boilers used thin steel plates calculated to contain required steam pressure with minimal material costs, their designers relying on mathematical precision to achieve adequate performance at competitive prices. Sullivan ordered boiler plates 1/4 inch thicker than engineering tables recommended, then specified hand-riveted construction methods that added both weight and manufacturing time to the assembly process. The steam cylinders that would power the lifting mechanism received similar treatment. While European designs used cast iron components sized to generate necessary lifting force, Sullivan's specifications called for steel cylinders bored to tolerances that exceeded operational requirements. The piston rods were machined from solid steel bars rather than hollow tubing, their diameter calculated not for adequate strength, but for permanent durability under conditions that would destroy lighter construction. Heinrich Müller visited the Bay City factory in March of 1884, representing a consortium of European railroad equipment manufacturers interested in American crane development. He examined Sullivan's work with the methodical precision of an engineer trained at Technical University of Berlin, measuring component dimensions with calipers and calculating safety factors that seem to ignore established principles of economical design. Muller's slide rule confirmed what his experience suggested. The American derrick incorporated safety margins of 8-to-1, where European standards specified 3-to-1 ratios between working loads and component failure points. The revolving mechanism alone used enough bronze and steel to build 2 complete European cranes, while the Anzii steam plant generated power sufficient for machinery twice the specified lifting capacity. The mathematical analysis was undeniable. Sullivan's derrick would cost approximately 3 times more to manufacture than equivalent European equipment, require skilled operators familiar with high-pressure steam systems, and consume coal at rates that made operational costs significantly higher than hand-powered alternatives. Muller documented these findings in reports to German engineering journals, concluding that American manufacturers were building industrial monuments rather than practical railroad equipment. But Sullivan understood requirements that European experience had never encountered. Michigan mining operations had taught him that mechanical failure under emergency conditions meant human death, not simply operational delays and repair costs. The steam shovels he had maintained in copper country operated in conditions that would disable lighter equipment within months, their overbuilt construction providing the reliability necessary for continuous operation in hostile environments. The assembly process reflected this philosophy of permanent construction. While European manufacturers used standardized components produced by mass manufacturing methods, Sullivan insisted on hand fitting major assemblements to eliminate the clearances and tolerances that would cause wear and failure over extended operation. Bronze bearings were individually machined to precise dimensions, then packed with grease formulations designed for decade long service intervals rather than seasonal maintenance schedules. The revolving mechanism represented the most complex engineering challenge, requiring a turntable capable of supporting 45 tons while rotating smoothly under full load conditions. European crane designs typically limited rotation to partial arcs, using fixed mounting systems that simplified construction at the cost of operational flexibility. Sullivan's specifications demanded full 360-degree rotation with steam-powered control systems that could position loads within inches of intended destinations. By September of 1884, the first industrial works steam wrecking derrick stood completed in the Bay City Assembly Bay, its massive proportions dwarfing the railroad flat car that would transport it to operational sites. The machine incorporated design elements that European observers classified as American excess. Structural members sized for loads far beyond operational requirements, steam systems capable of continuous high-pressure operation, and control mechanisms that provided precise load positioning through infinitely variable steam cylinder operation. Testing revealed capabilities that justified Sullivan's over-engineering approach. The derrick could lift 20 tons to full boom extension while maintaining perfect load control, lower massive components with precision measured in inches rather than feet, and operate continuously for 12-hour shifts without mechanical stress or component fatigue. Steam power eliminated the crew coordination problems that plagued rope and pulley systems, allowing single operators to position loads that previously required teams of 20 men working in dangerous coordination. The completed machine represented engineering philosophy that prioritized permanent capability over immediate cost considerations. Every major component was designed for indefinite service life, with maintenance access that allowed field repairs using standard railroad shop equipment. The boiler could burn coal, wood, or oil depending on local fuel availability, while steam systems incorporated redundant safety features that prevented the catastrophic failures that had killed operators of less robust equipment. European engineering consultants acknowledged the derrick's impressive lifting capacity while questioning whether such mechanical complexity was economically justified for railroad wreck clearance operations that existing methods could eventually accomplish through patient application of adequate labor. Thomas Wright received the telegram at 2:17 on the afternoon of November 15, 1896, while supervising routine track maintenance near Harrisburg. The message from Pennsylvania Railroad Dispatch contained details that made his 20 years of wreck clearance experience seem inadequate. Locomotive number 407 and 6 freight cars had derailed at Dutchman's Curve, the engine weighing 100 tons and lying on its side across both tracks, with steam still venting from ruptured boiler lines. Wright commandeered the next eastbound freight train, knowing that conventional clearance methods would require at least a week of coordinated labor to reopen the critical freight corridor between Philadelphia and Pittsburgh. His mental calculations were grim. 200 men with ropes and pulleys could eventually right a locomotive through systematic application of mechanical advantage, but the process demanded careful rigging at multiple anchor points, coordinated pulling by teams of horses, and incremental movements measured in inches rather than feet. The wreck site revealed destruction that exceeded Wright's worst estimates. Locomotive 407 had rolled completely over during derailment, its massive driving wheels pointing skyward, while the boiler and firebox remained partially buried beneath tons of freight car debris. The tender had separated during the accident, scattering 20 tons of coal across a 100-yard radius, while twisted rails and splintered ties created obstacles that would complicate any attempt to position conventional lifting equipment. European railroad authorities had established proven procedures for such accidents through decades of practical experience. British manuals specified sequential dismantling of freight car components to provide access to locomotive lifting. Points, followed by systematic rigging using manila rope and hardwood blocks rated for calculated loads. German engineering doctrine required precise measurement of weight distribution and center of gravity before attempting to reposition overturned locomotives through coordinated human effort. Wright began implementing these time-tested methods, directing crews to clear debris and establish anchor points for the pulley systems that would eventually generate enough mechanical advantage to lift the locomotive. The work proceeded with methodical precision as the teams positioned blocks and tackles at optimal angles, their calculations based on engineering tables that specified exact rope tensions and pulling forces for various locomotive configurations. But at 4:30 that afternoon, the distinctive whistle of an approaching steam engine interrupted Wright's preparations. The industrial works derrick arrived on a specially reinforced flat car, its massive proportions immediately dwarfing the conventional equipment that Wright had been positioning around the accident site. The machine's 45-ton bulk required careful unloading using temporary track sections that distributed its weight across multiple railroad ties. Daniel Eels supervised the derrick's deployment with the systematic precision of an engineer who understood that mechanical failure during rescue operations meant human catastrophe. The steam plant was fired and brought to operating pressure, while crews positioned outrigger supports that would stabilize the machine during lifting operations. Unlike rope and pulley systems that required extensive rigging time, the steam derrick could begin work immediately once positioned and pressurized. Wright watched with professional skepticism as the derrick's boom extended over the overturned locomotive, its steam-powered controls allowing precise positioning that eliminated the coordination problems inherent in multi-team pulling operations. European methods required constant communication between rope crews stationed at different anchor points, their efforts synchronized through whistle signals and hand gestures that became unreliable under emergency conditions. The steam derrick's lifting chains were attached to locomotive 407 at 3:45, with Eels personally inspecting each connection point to ensure proper load distribution. The machine's bronze bearings allowed smooth rotation under full load, positioning the boom at optimal angles, while steam cylinders provided the infinite control necessary for safe lifting operations. Wright had never witnessed machinery capable of such precise load manipulation, watching tons of twisted metal respond to operator commands with precision measured in inches. At 4:02, the derrick's steam cylinders began their slow extension, lifting the 100-ton locomotive with steady power that eliminated the jerky, uncontrolled movements characteristic of rope and pulley systems. Wright observed load behavior that defied his experience with conventional methods. No sudden shifts in weight distribution, no dangerous swinging motions, and no requirement for crews to work beneath suspended loads while repositioning rigging equipment. The locomotive rose slowly but steadily, its massive bulk rotating as steam power overcame gravitational forces that would have required coordinated effort by hundreds of men using traditional methods. By 5:15, locomotive 407 sat upright on temporary supports, its damaged components accessible for inspection and repair. The derrick had accomplished in 73 minutes what Wright's conventional methods would have required 3 days to achieve. Freight car clearance proceeded with similar efficiency as the steam derrick methodically lifted each derailed component, positioning the twisted remains beside the track corridor to allow track repair crews immediate access to damaged rails and roadbed. By 8 o'clock that evening, the main line was clear and ready for traffic, a result that European methods could not have achieved in less than a week of intensive labor. Word of the Dutchman's curve operation spread through American railroad networks with the speed of telegraph communication. Railroad executives who had questioned the economic justification for steam powered lifting equipment suddenly faced operational reality the conventional cost analysis had failed to anticipate, time savings that measured not in labor hours, but in revenue lost during line closures, freight delays, and passenger service interruptions. Cornelius Vanderbilt received detailed reports of the Pennsylvania operation while reviewing New York Central's equipment requirements for the coming winter season. His calculations revealed brutal mathematics that European engineering consultants had overlooked. Major freight corridors generated revenue measured in thousands of dollars per hour, making rapid wreck clearance an economic necessity that transcended simple equipment costs. Orders began arriving at industrial works within days of the Dutchman's curve demonstration. Baltimore and Ohio Railroad requested immediate delivery of a 30-ton capacity derrick, while Chicago and Northwestern specified a 50-ton machine for operations in the grain-heavy freight territories of the upper Midwest. By December of 1896, Eels had accumulated enough orders to justify expanding his Bay City manufacturing facilities to accommodate production schedules that European competitors had never imagined economically viable. The American approach to railroad wreck clearance had demonstrated superiority that mathematical analysis alone could not have predicted. The orders that arrived at industrial works during the winter of 1897 challenged every assumption about practical crane capacity that European engineering had established. Santa Fe Railroad requested a derrick capable of lifting 100 tons after a collision involving two locomotives had created wreckage too massive for existing equipment to handle. Great Northern specified machinery that could operate reliably in Montana winter conditions, where temperatures reached 40 below zero, while Southern Pacific demanded steam plants capable of burning low-grade California oil when coal supplies proved unavailable in desert territories. Eels responded to these demands by abandoning conventional wisdom about crane scaling limitations. European authorities had concluded that steam-powered lifting equipment became impractical beyond 50-ton capacity due to the exponential increase in structural weight required to support heavier loads. German engineering manuals specified maximum boom lengths and lifting radii based on metallurgical calculations that assumed rational limits on component sizing and manufacturing costs. Sullivan's design team ignored these constraints entirely, developing structural specifications that treated each new derrick as though it would operate continuously for half a century rather than the typical 10-year service life that European manufacturers considered adequate. The 100-ton derrick ordered by Santa Fe incorporated main boom assemblies built from steel I-beams that weighed more than complete European cranes, while boiler specifications called for pressure vessels capable of generating steam for 12-hour shifts without requiring water or fuel replenishment. Manufacturing these giants required fundamental changes to industrial works production methods. The company's existing foundry capabilities proved inadequate for casting bronze bearings, large enough to support 100-ton loads while maintaining smooth rotation under operational stresses. Sullivan designed new furnaces specifically for producing bearing assemblies that weighed individual tons, their bronze content representing more raw material than most European crane manufacturers used for complete machines. The structural steel requirements pushed American metallurgy into territories that European suppliers had never explored. Main boom components required steel sections with load-bearing capabilities that exceeded anything previously manufactured for mobile equipment, while turntable assemblies demanded precision machining on scales that challenged existing industrial capabilities. Each derrick consumed enough steel to build a substantial railroad bridge, yet maintained the mobility necessary for rapid deployment to accident sites across thousands of miles of railroad network. By 1904, Industrial Works was delivering derricks with capabilities that seemed to violate basic engineering principles. The 150-ton machine built for Pennsylvania Railroad weighed 90 tons itself, requiring specially reinforced flat cars for transportation and track modifications to accommodate its massive proportions. Its steam plant generated enough power to operate multiple conventional cranes simultaneously, while control systems provided precision that allowed operators to position locomotive-sized loads within inches of intended destinations. European observers documented these developments with mounting incredulity, calculating component safety factors that exceeded 10-to-1 ratios between working loads and structural failure points. Heinrich Müller published detailed analyses in German engineering journals, arguing that American manufacturers were building industrial monuments rather than practical railroad equipment. His cost calculations revealed that single Industrial Works derricks incorporated enough material and manufacturing time to produce 5 equivalent European machines. But operational results vindicated Ehl's over-engineering philosophy in ways that theoretical analysis could not predict. Railroad maintenance chiefs discovered that steam derricks built in the 1880s continued operating with reliability that European equipment could not match after 20 years of service. Boilers designed for indefinite operation required only routine maintenance, while bronze bearings packed with specialized grease formulations showed no measurable wear after lifting millions of tons through decades of emergency operations. The economic mathematics proved equally compelling. Pennsylvania Railroad's chief mechanical officer calculated that derrick number 43, built in 1891, had cleared over 2,000 accidents during 15 years of service, while consuming maintenance costs that averaged $12 per month. European equipment purchased during the same period had required major overhauls, component replacements, and early retirement due to structural fatigue that American over-engineering had eliminated through sheer material excess. Sullivan's maintenance philosophy contributed significantly to this operational longevity. While European manufacturers designed equipment for replacement after predictable service lives, Industrial Works derricks incorporated maintenance access that allowed complete rebuilding using standard railroad shop equipment. Steam cylinders could be rebored and fitted with new pistons, boiler tubes could be replaced individually, and structural components could be repaired through welding techniques that restored original strength specifications. The company's field service program reflected this commitment to permanent operation. Trained mechanics traveled established circuits, performing preventive maintenance on derricks scattered across American railroad networks. They carried complete inventories of wearing parts, specialized tools for steam plant service, and technical expertise that allowed major repairs at remote accident sites. This support system eliminated the operational downtime that plagued European equipment when specialized factory service became necessary. By 1922, Industrial Works had delivered its masterpiece, a 200-ton capacity derrick that represented the absolute pinnacle of steam-powered lifting technology. The machine weighed 150 tons, incorporated steel structures that required architectural engineering methods to calculate load distributions, and consumed coal at rates that made its operation economically justifiable only for the most catastrophic railroad accidents. This ultimate derrick could lift complete locomotives without strain, position 100-ton loads with surgical precision, and operate continuously for 24-hour periods when emergency conditions demanded sustained performance. Its construction required 3 years of manufacturing time, consumed enough steel to build a substantial factory building, and cost more than most railroad companies spent on conventional equipment during entire fiscal years. European engineering authorities acknowledged American achievements while maintaining that such mechanical excess represented economic irrationality rather than technical progress. British railway journals published detailed cost analyses proving that conventional methods could accomplish identical results through patient application of adequate labor, while German technical universities used American derrick specifications as examples of engineering decisions that ignored rational economic constraints. Yet American railroads continued ordering these massive machines, their executives recognizing operational capabilities that transcended simple cost benefit analysis. A 200-ton derrick could clear the most catastrophic accidents in hours rather than weeks, restore critical freight corridors to service before competitive transportation could capture diverted traffic, and maintain American railroad supremacy through mechanical capabilities that European infrastructure could not match. The age of American over-engineering had reached its zenith in machines built to last generations. The modernization campaign began at Pennsylvania Railroad headquarters in 1947 when efficiency consultants armed with post-war manufacturing philosophy declared steam-powered equipment obsolete compared to diesel alternatives that promised reduced operating costs and simplified maintenance requirements. Chief Mechanical Officer Robert Harrison reviewed proposals for diesel-powered derricks that weighed 30% less than equivalent steam machines, started instantly without firing procedures, and eliminated the skilled firemen that steam operation required. The economic analysis seemed irrefutable. New diesel derricks cost $6,000 compared to $12,000 for steam equivalents, required minimal operator training, and consumed fuel only during actual lifting operations rather than maintaining continuous steam pressure for emergency readiness. Accounting departments calculated immediate savings in labor costs, fuel consumption, and equipment depreciation that made diesel conversion appear financially inevitable. Harrison authorized the first diesel derrick purchases in 1948, beginning systematic replacement of steam equipment that railroad management classified as outdated technology from a previous industrial era. The gleaming new machines arrived with manufacturer guarantees, operator manuals simplified for general maintenance personnel, and hydraulic systems that eliminated the complex steam plant knowledge that had become increasingly difficult to find among younger railroad workers. By 1955, Pennsylvania Railroad had retired over half of its steam derrick fleet, selling the massive machines to smaller railroad companies or industrial scrap dealers who valued their bronze components and high-grade steel construction. The remaining steam derricks were relegated to secondary routes and non-critical operations, their continued operation viewed as temporary necessity until complete diesel conversion could be achieved. But operational reality began contradicting theoretical efficiency within 5 years of the modernization program. Maintenance Chief William Patterson discovered that diesel derrick number 107, purchased in 1949, required its first major overhaul in 1954 after accumulating only moderate service hours. Hydraulic seals had failed due to contamination from railroad dust and moisture, while diesel engines designed for truck applications proved inadequate for the sustained high-load operation that wreck clearance demanded. The hydraulic system failures revealed fundamental design compromises that steam technology had never encountered. Diesel derricks used complex hydraulic circuits with dozens of seals, valves, and precision machine components that required factory-level expertise to repair properly. When hydraulic pumps failed during emergency operations, the machines became completely inoperable until specialized technicians could perform system rebuilds that often required shipping major components back to manufacturers for reconditioning. Patterson's maintenance records documented a troubling pattern of premature component failure that contradicted manufacturer promises of simplified operation. Electronic control systems, introduced to provide precise load positioning, proved vulnerable to moisture and vibration that steam mechanical controls had ignored for decades. Diesel engines required complete rebuilds at intervals that steam boilers handled through routine tube replacement and boiler washing procedures that railroad shop forces could perform without outside assistance. Meanwhile, steam derrick number 23, built by Industrial Works in 1887, continued operating with mechanical reliability that embarrassed newer equipment. The machine had lifted millions of tons during 70 years of service, while consuming maintenance costs that averaged less than $200 annually. Its bronze bearings showed minimal wear despite supporting countless heavy loads, while the boiler required only routine inspections and occasional tube replacement using standard railroad shop procedures. The economic comparison became increasingly stark as diesel equipment aged beyond warranty periods. Patterson calculated that diesel derrick maintenance costs averaged $4 per ton lifted during their operational lives, while steam derrick number 23 had achieved lifetime costs of 12 cents per ton through 7 decades of continuous service. The supposedly efficient modern equipment was consuming maintenance budgets at rates that made the obsolete steam machines appear economically superior. Railroad executives began questioning the modernization philosophy as diesel derricks purchased in the early 1950s reached retirement age while steam equipment built during the 1890s continued reliable operation. The promised simplicity of diesel operation had proved illusory, requiring specialized hydraulic technicians whose expertise cost more than the firemen that steam operation had employed. Electronic controls that were supposed to improve precision had introduced failure modes that mechanical steam systems had never experienced. By 1960, the maintenance cost differential had become undeniable. Chief Mechanical Officer Patterson compiled comprehensive operating statistics revealing that steam derricks built before 1920 averaged 95% availability rates after 40 years of service, while diesel equipment manufactured during the 1940s showed 70% availability after only 15 years of operation. The over-engineering that European critics had dismissed as American excess was delivering operational longevity that modern efficiency philosophy could not match. The final vindication came through economic analysis that railroad accounting departments could no longer ignore. Steam derrick number 23, purchased for $8,000 in 1887, had operated continuously for 73 years while generating total lifetime costs of $6,000 in fuel, maintenance, and crew wages. The diesel replacement purchased for $6,000 in 1952 had already consumed $12,000 in maintenance costs while requiring complete overhaul after 8 years of service. Patterson's recommendations to halt further steam. Derrick retirements came too late to save most of the fleet. Pennsylvania Railroad had already scrapped dozens of machines that could have operated reliably for additional decades, their bronze bearings and high-grade steel construction representing material value that exceeded the cost of many complete modern derricks. The few remaining steam machines continued working until skilled firemen became unavailable and boiler inspection requirements made operation impractical rather than mechanically impossible. The last operational industrial works steam derrick was retired from Pennsylvania Railroad service in 1978 after 91 years of continuous operation that had spanned 2 world wars, the Great Depression, and the complete transformation of American railroad technology. The machine was donated to the Railroad Museum of Pennsylvania, where it remains on display as testimony to engineering philosophy that prioritized permanent construction over quarterly profit optimization. Railroad historians would later calculate that American steam derricks built between 1885 and 1925 achieved average service lives exceeding 60 years, while diesel replacements manufactured during the modernization period averaged 25 years before requiring retirement. The over-engineering that contemporary critics had dismissed as wasteful excess had delivered operational longevity that modern efficiency methods could not achieve, proving that permanent construction ultimately costs less than repeated replacement of equipment designed for planned obsolescence.